We're going into the wild, into the wild. If the world is ending, we better have some fun.
Good morning. I had to take the video for myself. So very, very happy and excited to be here, and thank you for coming. Part of the thing that also Michal mentioned is the theme of camping, and I think camping teaches us one simple rule. Preparation comes before the weather, and you don't need to wait for the rain to start building your tent. And this is also what we need around in cybersecurity, the same lesson. Preparation comes before the threat, and part of the thing is quantum is coming, and part of the thing is we need to come and start preparing for this journey. And this is the post-quantum security journey that hopefully will take this trail and path together now. We started at Microsoft 4 years ago, this journey, and part of the aim of this talk is to make sure that you are aware of what's coming and also what is quantum. We understand that systems are vulnerable. You probably heard about harvest now, decrypt later, and decrypt later is becoming sooner and sooner, and this is why we will start this journey, and hopefully the journey to post-quantum is a multi-year journey, and we urge you to start it as soon as possible. Part of the things that we saw up to last year is that we need around 1 million qubits of a quantum computer to be able to crack RSA or asymmetric encryption. And this was last year, and if you know, by the end of 2025, we had the largest or the biggest quantum computer around the world was around 1,300 qubits. So you say, okay, 1,300, 1 million, it's a decade ahead. So suddenly things are changing, and we started to see and experience an acceleration in the last year. So from 1 million qubits, and part of the thing that we have is, if we needed 1 million qubit at the end of March, suddenly we had something happening. It's 10,000 qubits. And we had a 100 times reduction in less than 14 months. And this is an exponential acceleration. And it means that the threat is coming closer. And if, again, part of you build a tent while the sky is blue, so we're starting to see the storm clouds on the horizon coming towards us. And this is part of the thing that I want to discuss. So we know that symmetric encryption is quite safe. Usually it's brute force, and it's on the longer horizon, a much longer horizon for quantum computers to risk it, to threaten it. But PQC for asymmetric is already here, and we understand, and probably you're following the news of the last years, we're starting to see the smallest quantum computers starting to challenge the lower RSAs. And this is part of the thing that we saw. And I won't go into all of the details, but the time horizon with the quantum computer was to break strong RSA within weeks, but you had 10 million qubits, and the symmetric encryption was on a century time horizon. But this is, again, part of the thing that I want to hopefully change your mind here. And this is why we are going to jump into the quantum world, and I want to start to explain what are quantum computers, what are the risks, and especially that you'll come out of here understanding quantum. And AI, generative AI, took the attention of most of the world, but quantum computing is evolving rapidly. And this is why we're starting BlueHat with a focus on quantum computer and maybe the rising threat around it. So, a word of advice before going on this camping. Richard Feynman, 2 times Nobel laureate in physics, one of the founding fathers of quantum mechanics, said, "It is safe to say that nobody understands quantum mechanics." And even Niels Bohr, the founding father of quantum mechanics, said, "Everything we call real is made of things that we cannot be regarded as real." And we're going to go on a very, very weird trail, counterintuitive. It's nothing as we learned in classical physics in high school, or even if you took a few physics courses at university. And this is my challenge. If I cannot explain it simply enough, maybe I do not understand it good enough. So hopefully you will understand as much as possible throughout and by the end of this deck. So we're starting to see that generative AI is accelerating and changing the world. We started to see autonomous vehicles in the US, some in Europe. And we understand that we have already robots are also accelerating. But what will happen with quantum and the advances that we saw in science fiction series, movies, books? We cannot imagine the world after quantum or after AGI or ASI. And part of the thing that we need to start imagining it. We don't just build a bridge, we need to understand what is going to be at the other end of this bridge. And this is part of the challenge here. And if you're following the headlines from 2020, so it started with COVID, and also my journey with quantum started with COVID. I took the first lockdown to start programming quantum computers, and it's very, very weird. So we have headlines across the news throughout the last 6 years, and the rapid advancements of the news cycles and news titles and news items are increasing. This is from April, and suddenly we are finally doing something useful. And this is also from the last week. We had a few breakthroughs in quantum computers that we're starting to see that they are able and capable of solving real-world problems. If you're following science fiction, whatever and whenever we don't want or cannot explain it, we just stick quantum in it. Dark magic, very, very deep science, stick quantum in it. And maybe you followed also Marvel, the quantum world, Quantumania. So it's starting to be more in the attention and the awareness, and even popular culture. 4 years ago, we started to see quantum computers in TV series, science fiction TV series. So it's here. It's starting to be here. And this is part of the journey that we need to understand. And the first gateway to quantum is the dual nature of light. You see here the lights, you see me, but in classical physics, light can be either a particle or a wave. And suddenly in quantum, it can be both. And this dual nature of light is the basic of quantum mechanics, but also for quantum computers, we will use this duality, a superposition, both 1 and 0 together. But this is the dual nature of light. It's paradoxical in classical physics, but in quantum, it's fundamental. The next phase, and we'll go through a bit of quantum mechanics, interference. So as Michal encouraged you to meet, interact, speak with each other, create a community, also when waves meet or they don't pass by, they interact. Whether constructively, if they are synced and aligned, so we build better waves, larger waves, like you're seeing also in harmonics, in singing, when the voices align, you hear the choir much better, or when they are out of sync, they cancel out each other. And this is the basic foundation or phenomena that quantum computers and quantum algorithms are using, that we need to be able to find or to amplify the correct answer and to cancel out the wrong answer in quantum computers or through quantum algorithms. So this is the basic phenomena for us. But it's not only quantum. I want to show you this. I took around 3 months ago when I came back to Israel over Tel Aviv. Probably most of you are familiar with this phenomena on the beach, and we don't know if it's a bug or by design, but it's interference. The waves or the current in the Middle East, the Mediterranean, comes counterclockwise from Egypt towards Israel, towards Lebanon, Syria, and Turkey, and it carries all of the sand that we have is from the Nile Delta. So suddenly, we have these waves interacting. When they come through these wave breakers from the two sides, suddenly they are out of sync. The wave breaker changes their amplitude and they cancel out. Destructive interference. And if they cancel out, they stop on the spot, and the sand that they are bringing just sinks, and then we create more real estate or more beach line. You don't see it in other beaches across Israel, so probably it's a bug in the design. If they took it maybe 3 to 4 meters into the sea, it would not have happened. But this is something that we see in the classical world. David Ben-Gurion, the founding father of Israel, spoke about it at the end of the 50s. He did a deep dive into AI just a year after it was coined in 56, and also into quantum mechanics. And he said, the microscopic world cannot be understood in the macroscopic world. And this is the language that we do not have to explain it, but sometimes we try to see other phenomena that exist in this type of world. You saw the trees, so outside they're of plastic, but you have probably plants at home, at the office, at your garden, on your balcony, and plants or nature uses quantum effects and quantum calculation to live, to grow, to flourish. Also us, not only plants are doing photosynthesis, also we are doing photosynthesis. Photosynthesis, photons, the particles, not the waves, interact with us, and we can create or synthesize vitamin D. And plants do photosynthesis for energy, for living. So part of the thing is, how do we take these quantum effects that are just outside the window in your office and move it to us, to control them and start using this type of calculation, how nature calculates for us?
There was a time when the newspaper said that only 12 men understood the theory of relativity. I don't believe there ever was such a time. There might have been a time when only one man did, because he's the only guy who caught on before he wrote his paper. But after people read the paper, a lot of people kind of understood the theory of relativity in some way or other. But more than 12. On the other hand, I think I can safely say that nobody understands quantum mechanics. Now, if you appreciate this and don't take the lecture too seriously, then you really have to understand it.
So part of the thing, Richard Feynman, again, 2 times Nobel laureate in physics, one of the best scientists in the 20th century and also the best explainer of science, says that nobody understands quantum mechanics. And this is part of the weird part. And as we dive deeper, I want to move from the bit to the qubit. The bit is the fundamental unit of us, of how do we store and use data or information. 0 and 1, the slides on your phone, the computer streaming, everything is with bits. Claude Shannon invented this bit, and also just closing the circle, Anthropic Claude is called after Claude Shannon, who invented the bit, to a qubit, quantum bit. So how do we use this logical concept of information and move it to a quantum bit? So we need to simulate. And I want to show you just the order of magnitudes, how they scale, because bits are not qubits. And I will explain it shortly. So if we take 20 qubits, it's like 16 megabytes of memory, and we can simulate it probably on a smartphone. But if I increase it to 30 qubits, suddenly it jumps to 16 gigabytes. So maybe a strong laptop can still simulate. But what will happen if I move it to 50? Suddenly it's 16 petabytes. So we need a very strong computer, and also this is the limit of classical computers, that they cannot simulate any further or above 50 qubits. And this is part of the limit. And the qubits to the bit, 50 qubits is 2 to the 50 bits, okay? If I would say 50 bits, you would say it's nothing. But 50 qubits, it's 2 to the power of 50 bits, okay? And every qubit I add, it doubles the strength or the power of the computer. And this is another politician that I want you to hear.
Computing, but when do you expect Canada's ISIL mission to begin again? And are we not doing anything in the interim while we prepare?
Okay. Very simply, normal computers work by... No, don't interrupt me. When you walk out of here, you will know more. Well, no, some of you will know far less about quantum computing, but most of you, normal computers work either there's power going through a wire or not. It's 1 or a 0. They're binary systems. What quantum states allow for is much more complex information to be encoded into a single bit. A regular computer bit is either a 1 or a 0, on or off. A quantum state can be much more complex than that, because, as we know, things can be both particle and wave at the same times, and the uncertainty around quantum states allows us to encode.
So I wish we had more politicians who can explain science. So 1935, Erwin Schrödinger, again, one of the founding fathers of quantum mechanics, and we're at the second quantum revolution. The first quantum revolution was exactly 100 years ago, at the 20s of the 20th century, that humanity built the foundations and understood what is quantum mechanics. This time, 100 years later, in the second quantum revolution, we take the science into the engineering. It's still deep tech, but it's already engineering. But part of the thing that he tried with this thought experiment, probably all of you know Schrödinger's cat, it was trying to explain the microscopic or the quantum world in the classical world. So I took the cat and, as a thought experiment, close it in a box, have a vial with poison and a material, radioactive material that decays, and it might break the vial and the poison will spill out and kill the cat. So the idea was that until I do not open the box, I do not know if the cat is dead or alive. So it's in superposition, both dead and alive. And until I open and look, only then I will know. And this duality is also part of the thing that the weirdness of quantum, that Einstein had a few issues with this theory, because this is the weirdness that we are part of the quantum system. So we cannot disengage. We are part of the world, so if I watch, I change the interaction. And this is also part of the thing that Einstein said, what do you mean? If a rat goes into my lab and looks into my experiment, it will break the experiment? So this is part of the weirdness of quantum mechanics, that the observation, collapses the quantum state from a wave to a particle, or vice versa. And maybe you had this situation at home, that until we do not open the cupboard, they are both broken and whole together. So this is part of the thing that we're trying to explain in the classical world. So what is a bit and what is a qubit? The bit, again, it's something that we invented, 0, 1. You have current, you don't have current, on and off, lights on, darkness. We know it, but let's take the qubit. And suddenly a quantum bit is not a logical or an invented particle or invented notion that we invented. It's a physics particle. It's an ion, it's a photon, it's an atom that we are doing calculation on top of it. So this is why it is described as a sphere, because it is infinitesimal small, but it is still a sphere, an ion, an atom, a photon, and we're doing calculation over or on top of it and using it. So it can be either 0 and 1, or both 0 and 1. So this is part of the exponential growth of the computing power, that we can have both 0 and 1, but actually it's more, because the quantum state can be not only 0 and 1, it can be almost any value in between. So it means that we have real strong and exponential increase in the computing power of quantum computers. But again, we need to control nature. It means that how can I take a single atom, engineering-wise, science-wise, and control it and spin it, or even a single photon or a single ion, and try to use it. And this is the last physical phenomenon that I want to explain, entanglement. It's how do we take two qubits and connect such a strong bond that I will know the state of, if I know the state of one, I will know immediately the state of the second one, no matter the distance, even if it's hundreds or thousands of light years away. And this is why Einstein called it spooky action at distance, because he said, nothing can break general relativity. Nothing can be faster than the speed of light. So how can it be that I have a qubit here, and maybe a qubit 10 light years away, and the minute or the second or the microsecond that I know the state of this qubit, I will know what is going on 10 light years away from here. So does it break general relativity? This is why he called it spooky action in a distance, and many very cool experiments try to prove that there are no hidden variables there to show it. And I'm going back here. Richard Feynman, he's also the one that invented the concept of quantum computers. He said, if nature calculates quantum, why can't we use this magnificent machine and calculate? Can we use it to create a digital twin of nature, of everything? Because even if we calculate today weather forecasts, everything is deterministic. And this is why forecasts are off, because nature is not deterministic, and we do not really know how to simulate nature end to end. But suddenly we have quantum computers. And this is part of the thing that maybe you started to see these chandeliers, the way the quantum computers, most of them look. And this is also the thing that you're starting to see in science fiction series or movies. So this is the famous chandelier. So we will go over it soon, but suddenly from the quantum world, we understand if I'm taking one particle, okay? I need to stop. I need to stop nature. I need to freeze nature. And this means that nature freezes only in the absolute zero, minus 273 Celsius degree, okay? In the absolute zero, nature freezes. No particle moves. And if I can reach this temperature, I will be able to control a single atom, a single ion, or any other almost particle. Quantum computers are working at 5 millikelvin, so 5,000 of a degree, 5,000 of a degree above absolute zero, that we need to stop nature and to freeze nature. Deep space is only around 1 Kelvin. It means that it's 100 times colder than deep space quantum computers. And this is also part of the challenge that how do we freeze it? We won't go into it, but we need to understand that we need to freeze or stop nature to be able to calculate. This is one of Microsoft's computers. So this is the computer itself. And this is called the dilution refrigerator. It means that we need to reach 5 millikelvins throughout this computer. And part of the thing, like fire is also quantum. If you're going to camping, fire is quantum. The chemistry of fire is quantum effect. The light, the energy, the photons that are emitted, everything is quantum, but it's unstable because the flame interacts with nature, with us, with the environment. So if it interacts highly with the environment, the quantum effects decohere. They're ruined. So we cannot have a quantum computer that is like fire, very, very unstable. So we need to freeze it that it will not interact, or as much as possible will not interact with the environment. So this is why we need everything to be stable, very, very cold, no noise, but even a single, maybe from a cosmic radiation, a single neutrino can pass by and ruin your experiment or decohere the quantum state. So this is why they are very, very unstable here. Part of the thing that we have around 6 architectures of quantum computers. In the regular classical computers, the CPU, we have one architecture overall, but we have ion traps. So how do we catch one ion and control it? We have superconducting qubits. We have linear optics, so I'm using photons as my qubits. Envy centers, part of the thing that is very, very weird in quantum. So I can take a diamond and I can remove one carbon atom. So suddenly I have a hole in the crystal, and this gap in the crystal behaves like a particle, and I can use the gap as a particle, okay? Very, very weird stuff. Quantum dots, so if you have a Samsung TV, they are using also quantum dots for various other effects, and the topological qubit. This is where Microsoft invests and invested for many, many years. And this is part of the weirdness of the topological qubit, because Microsoft, part of the thing outside is maybe gambled on an anion. Anion is, again, part of the weirdness. Again, excuse me. Anion is a quasi-particle, so it's not even a particle. It's a physical phenomena that behaves like a particle. But part of the noise, that they are very, very noisy, the computers, and up to last year, we call these computers NISQ, N-I-S-Q, Noise Intermediate Scale Quantum. Quantum computers that are very noisy, meaning they are very, very unstable, and I cannot do long calculations or long compute on them. And today we moved, between 2025 and 2026, we moved to quite stable quantum computers that are much more stable, and this is part of the anion that is also two-dimensional, but it's very, very weird. I will show you soon. So this is here at February 2025, Microsoft introduced or unveiled the Majorana 1, the QPU. Like you have CPU, GPU, we have now QPU, quantum processing units. And part of the architecture and the fact of the anions, if we take any other architecture here, if I want to build a 1 million qubits computer, I need a computer around the size of a baseball stadium, okay? A huge one. Suddenly, Microsoft with the anions said, you don't need a baseball stadium. It's the size of the palm of the hand. I can fit 1 million qubits here in this part. And this was February 2025, the Majorana. For this, Microsoft had to invent a new state of matter. We know solid, liquid, gas, but it's not enough. To create the physical phenomena of the anion, we needed to create a new type of state. It's called the topoconductor. So I won't go into the physics, but it's very, very cool. A semiconductor and a superconductor, we are attaching them together. And once we attach them together with a special effect, in between them, a new state of matter is introduced, and we create the anyons, the topological qubits. Part of the thing that I will show you in the next slide, these wires are called nanowires. It means that they are one-dimensional wires. One atom, a row of one atom, single atoms in a row. So really single or one-dimensional atoms that we created. And part of the thing is the capability, and this is why it's the second quantum revolution. We're able now to create machines atom by atom. This is the control science engineering that we're seeing and we're experiencing. It's already not science fiction, it's science fact. The ability to print devices atom by atom and control everything around them. So how does it look? And just to go over the architecture of the computer, the QPU, almost on all architectures that you see the chandelier is at the bottom, the quantum processing unit. But a processor needs a computer to run, okay? So these are all the layers of the software, whether the CMOS and the operating system and the application and the services, and connecting it to the classical world. And this is also part of the thing, how we connect the classical world into the quantum world. And I want to give you a deep dive into how the Majorana 1 looks inside. Just to understand the dimension, this is single atoms, okay? Almost the number of pixels here, single atom nanowires that were able, and last year it was 8 qubits. So 8 doesn't sound a lot, but there are 8 that are stable. Usually it's logical qubits that we need around 100 or 200 physical qubits to create one logical qubit, because we need to average out all the errors. In classical computers, we know how to correct errors. We don't have errors almost, but we know how to fix them. How do we do error correction to nature? How do we do? Can we do? So this is also part of the thing that Microsoft chose the anion, because it's two-dimensional. One less dimension, so it's very, very, very stable. And even if we decohere 3 of the 3 corners out of 4, the qubit still operates and still stores the information non-locally. So this is part of the thing that we started seeing last year, and as I mentioned here, 1 million qubits at the palm of the hand, and it's accelerating, and this is part of the thing that we saw. We understand that quantum computers are very cool. Probably you will not have a quantum laptop or a quantum smartphone or a quantum Excel. We don't need it. But we do understand that quantum will work side by side classical computers, that the input and the output of quantum is classical because we work with bits, zeros and ones. So the input will be zeros and ones, and the output will be zeros and ones. So we will need the quantum machines operating next to regular computers, and we will just call the quantum computers to solve problems that we need quantum computers for. And this is also part of the very cool thing that we see in quantum and AI. They are using the same math. Linear algebra, the GPU, AI, and quantum computing or quantum mechanics are using the same math. This is why also we will see the acceleration around and part of the things that we see. Again, I mentioned that I started coding or programming quantum computers around March or April 2020, 6 years ago. Then it was on the gate level, okay, like assembler, 30, 40 years ago. Today, we have already a copilot that you can just take an image from an article, from a science paper. This is the quantum circuit that I want. Take a picture, and the copilot will write the code. This is here, and I really urge and recommend you to start coding quantum computers. It is very weird. There is no copy-paste. There is no delete. You are working on particles, so you cannot copy them and you cannot delete them. So it's very, very different how it interacts with everything. So this is part of the thing that why do we need them? We need a practical quantum advantage. It's not quantum supremacy. We need to solve something that is real, okay? And this is what the entire industry is trying to solve, something that either academics or industry will be faster and much better than classical computers. We have Azure, and even if you connect all of them together, there are still problems that we cannot solve. What do we need to do with it? So cryptography, I started handling it, and I will get back to it very soon. Quantum system simulations, we already see unbelievable improvements in classical systems using quantum simulations. Also optimization problem, of course, machine learning. We have QML, quantum machine learning, as I said it's very, very different. And part of the thing is to think of, it's not for big data problems. Quantum computers are solving small data, big compute, okay? This is the slogan. Taking 180 or take just traveling salesman, okay? To solve it for 5 cities, it's easy. To solve it to 30 or 40 cities, it's almost impossible, but it's only 30 cities, so it's small, but 2 to the 30, you understand that it explodes. And this is where we need quantum, when these problems are exploding during compute, and we need them to solve real issues. And this is just a few weeks ago, also in the Financial Times, what can quantum computers do for humanity? So also for the executives, it's on the table for everyone and anyone today. And this comes back to this. This is again from 2020, again, exactly 6 years ago, June 11th. Y2Q, you remember Y2K, it was called Y2Q, now Q Day, the day when we'll have a very strong quantum computer that can break asymmetric encryption, the end of privacy, the end of security, the end of whatever, national security, you can call it whatever you want, and people are preparing. DARPA started the challenge in 2016 to build the post-quantum cryptography, the math that cannot be solved by quantum computers. And this is part of the challenge that we see. And the challenge for us, for Microsoft, is that we have 4 hats. We build the quantum machines, the quantum computers, and I'll show you soon the progress that we've done in the last year. We manage a huge organization, more than 200,000 employees. We build the cloud, okay? So we also service systems that we need to protect and help the customers be protected. But also we are the security providers. Microsoft Security, you heard Michal, and you'll listen later on during the day and tomorrow also on MDash and other security solutions, but we need to address these 4 hats. And this is also one of our challenges. So in August 2025, we published our roadmap, the Quantum Safe Security Roadmap, that we started it again 4 years ago, 2023, and we're on the roadmap. And we mentioned that by 2029, by the end of 2029, all Microsoft services, technologies, products, solutions, infrastructure, everything should be quantum ready. It means that we will transfer to a hybrid encryption, both classical and PQC, but also to enable the customers, you guys, to enable it for your systems, for your customers, and help protect yourselves and the system. But this was, again, in August. Ancient history. 3 weeks ago, we unveiled Majorana 2. Part of the thing that Majorana 2 came is the combination of AI, generative AI is accelerating science, and it accelerated the development of Majorana 2, of the next QPU of Microsoft. We changed some of the hardware, the size is here, but by 2029, it's ready. So 1 million qubits by 2029, it means we need to prepare, okay? And this is part of the thing that we're starting to see not only in March in the acceleration of the neutral atoms, another architecture, but it means it's here. And if I'm starting to connect and everything to also Arthur C. Clarke, any sufficiently advanced technology is indistinguishable from magic, we're starting to see these clouds. And I started with camping, and part of the thing that you don't need to wait till the rain to build the tent. You need to start building it now. And this is part of the thing that you'll hear also across the 2 days, other talks about PQC and the things, but hopefully I was able to make it less black magic to you, that you'll understand that the road is here, okay? We need to start preparing probably soon. It's 2.5 years, up to 2.5 years we'll have, and this is again, an exponentially fast technology with the combination of AI that we are going to see a very, very different world, both for the positive, and we need to make sure that we will be able to protect our security, national security, and of course the privacy of the internet, of the users, of your customers, of yourselves, of everyone. So enjoy the trail.